machine learning for causality.
Wonderful. Thanks so much for having me. I understand you're very much interested in explainable things and understandable things and security. All these things are fundamentally about causality. And I'm not sure if I need to convince you of that. Like, for things to do things that we find unacceptable, they need to have a negative impact. Impact is not something we can predict. Impact is something related to causality. And I think this general phenomenon that all real prompts are actually prompts about causality. As data scientists, we usually treat them as if they were not prompts of causality. And there we have like an ongoing. And at the same time, if we understand the causal chains in a domain, we give the right explanations. Like, you can explain to me some simple system with a small number of parameters, but that's not what I'm interested in. I'm interested in the causal explanation. Why did that happen? What's the cause that leads to that? So this is a great opportunity for me to tell you a little bit about causality. So let's jump right in. If we look at what machine learning is currently good, machine learning is obviously very good at this task. Tell me this is a cat, those are my two cats. I just use this slide as a completely empty excuse to show you my cats, because like most people, I'm really excited. But also now we can look at large language models. They're really good at predicting text, making good text. They're not really good at producing positive causal influences on the world. And so we're good at these domains where the prompts are easily describable and where the causal links are relatively easy. If we talk about something like that, tell me what happened here and why. The causal link is much more complicated. You're really, really good at doing it. If we go into this broader space of what happened and why, machine learning still has a very long way to go, as long as it's out of domain in any meaningful way. So why are causal representations good? Now, if I could give you the correct causal description of something happening in the world, it may allow us to generalize better, because what things are really stable in this? Why do we do out of domain generally? Why are we interested in that? The real reason why we're interested in out of domain generalization is because the future is different than the past. And it's not just randomly different. We're not looking at, like, we have some data in some area, we want to do something about the vicinity. Not true. We have some data and we want to do something in the vicinity where the time arrow goes forward. And so there's a lot of things that will stay constant over time and other things stay not constant. For example, humans have certain causal powers. I can annoy you and you'll be annoyed back at me. That thing's going to be true in 50 years' time, just as well, unless we get out-evolved by some machine learning system, God forbid. Or a chair. I can sit down in the chair, and the chair will remain that affordance of being something that I can sit down on, and it's a causal power of the chair. Those causal things, they carry through into the future. Other things, like there's a certain number of chairs, and like most of them are empty right now, will not carry over into the future. Someone's going to give a talk here who's like really famous, and then all those chairs will be full. So causality or causal powers are one of these things that we really 100% can carry over into the future. That is reflected in human causality, in human cognition. So if you look at kids, they're not interested in predicting things. They're interested in causal chains, and you can show that in experiments. And so in general, if you look at humans talking with one another, you look at transcripts, how people talk with one another. Not what they do is they explain causal chains for one another. If you do this thing, then this thing happens because of this following business. Now, therefore, if we can move representation learning towards causal representation, we can learn faster, we can communicate them better, we can understand humans. Because even if causality wasn't a thing, if it's a thing for humans, if we want to interact with humans, we will need to use causal language, and it supports fundamental reasons. And there's, of course, therefore, a huge interest in the machine learning community to move towards causal representations. And
so maybe you will address them, but if I look at time series data and prediction, there is some causality built in that. So So that
I completely disagree with that statement. So it is true that we live in a world where there is some correlation at the human level of correlation and causation. But in lots of cases, people see their doctor and then they frequently die of something a little bit later. Does that mean that the doctor kills them? No, it means that they get sick. That makes them go to the doctor, and that makes them, and that ultimately makes them die. But it's not that the doctor kills them. And this kind of this problem of confounding. In fact, why don't you wait a few slides, because we're going to get exactly that at exactly that. Now, let's briefly review the cultures and everything. When I talk about the field of causality, it's all about avoiding confounding. It's all about avoiding factors that make correlation look like. So that's like your question is exactly the foundational assumption of the field of causality. Correlation is not causation. And let's go there a little bit. There's many different fields and they have different ways of approaching that. There's the field of sociology and economics. What they usually do is they say the world is complicated, everything's confounded, but there are these domains where I know something about the world. I can use these as little tricks to learn more about it. There are parts in the world where the world gives us something that's a little bit like a randomized control. Examples are quasi-experiments, RDDs, IVs, like if you're in that field. Then there's the field of medicine. The field of medicine basically says randomized control trials or go home. Why do they do that? They look back at a history where they looked at correlation and they found systematically that correlations have preciously little to do with causation, with things like socioeconomic status being a major confounder, but equally culture. Like, what do you know? German background people eat different food and they die of different causes. It's not really that their food kills them. The fact that like, how they socially deal with things, how they interact with the health system, there's like a million confounders. So in that sense, I'm thankful for medicine that it's not using machine learning to get it. Then there's epidemiology, that we have big data sets that try to understand what's happening. They have their own way of thinking. You probably heard of Julia Poll. Who heard of Julia Poll? Julia Poll, super popular, basically says, let's formulate causality really clearly. Julia Poll never in his school never worries about these problems that appear, not much. The problems that appear when you take these mathematical ideas and deal with them. Because what goes in is basically a set of conditional independencies. And the set of conditional independencies is not generally supported by the world. And econ has a wonderful history and culture of basically saying, you tell me these two things are conditionally independent. I don't believe it. Here's why I believe it's not true. And like they have a solid culture of that. Paul has done us a wonderful service at making this really clean, but he's not so worried about where the assumptions of his model. And then there's a branch of machine learning with people like Hugh Berryman and Bernhard Schulker, Joshua Bencher. They basically say, okay, let's make some assumptions about the world. Often, say in Schulker's work, you assume that things are non-Gaussian, non-linear, or independent. Also in David Lei's work, Decode you may have heard. You make strong assumptions about parts of the world, and then you can use machine learning to get a causality. And my own field, neuroscience, still believes that correlation is universal causation, but let's not talk about it. So let's talk a little more about cause effects. Now, an ideal RCT allows unbiased measures of cause effects. Why? We have a treatment and we have an outcome. We have lots of confounders, like we have lots of variables that could be confounders that could affect us, that can influence our outcomes. Why? But if we choose the treatment, if we randomize the treatments, it means that this variable effectively can be marginalized out and we can directly read out the causal influences. We can't read out the interactions of the causal influences with these external variables, simply because we wouldn't have them, but we can do that. So RCTs, it's very easy to prove that a randomized control trial is an unbiased estimator of the causal effects of the event. But well, the world often doesn't look like that. So I want to, and this gets you directly at your question. I have a variable x. I want to know that variable x affects variable y, but I have confounders z that affect x and y. And because they do, a correlation between x and y could be because x influences y, or it could be because z influences x and y. And you can directly see it's fundamentally impossible to distinguish this. If I don't know about these guys, it could be that there's any arbitrary effect, and it could just be the reflection that I then see in the relevant x. That's the effect of a confounder. Now, a lot of people in machine learning are like, well, but look, Konrad, we're entering the big data regime. We get so much data that eventually the confounders will go away. Like, I don't think it's true, because there's still a lot of things that we can't figure out, including maybe my thought processes that you fundamentally cannot figure out. But the second one is there's also colliders. Here we have a variable c, a collider. Variable c is affected by x and y. So if I do machine learning and I add z to it, I will generally get better at estimating my causal influence. That's the idea of removing confounders. But if I accidentally put my collider c into it, it produces a dependence of x and y, an apparent causal dependency, even if they're entirely independent of one another. So now we have this problem that we need to know what's a confounder, that's stuff that I should correct for, and what's a collider, that's stuff that I under no circumstances should correct for. In reality, it's often very hard to know which is which. I'm like, you're visiting the doctor. Is that a confounder? The doctor might give something to you, might affect some property of you, maybe how often you go to the doctor, and the doctor will also affect, like maybe how you affect the disease. Or maybe it's the other way around, that you see the doctor because of stuff. Like you are in the process of dying and you're not feeling good. And all of a sudden, like, and you're going, and the fact that you go to the doctor makes that clear, and then we have a measurement. So colliders and confounders are both important. Large parts of the causality field ignore colliders. That involves almost anyone who believes that throwing in lots of stuff into a machine learning algorithm ultimately makes confounders go away. It doesn't. But because you will accidentally, unavoidably affect colliders. Like whichever variables you have, they will ultimately feed into the variables that you measure. And therefore, then you can no longer correct them. And that happens even in economics, where the idea of a confounder is something that you universally talk about, but the worry about things being colliders is almost never stopped. Now, let me highlight. So I will be talking a lot about methods as they use in economics, about quasi-experiments. The reason is in observational causality, and like this, there's experimental causality, which means I randomize things, I see what happens causally. And then there's observational causality, you give me data and I try and figure out how things causally work. And I think that in general, the problem of observational causality is impossible. We'll be happy to defend that later when we discuss. But within the domain of observational causality, the quasi-experiments are the places where you can get closest to credible claims of causality. So let's talk about that. So in instrumental variables, we're in the same setting as before. We have a variable z. Then when I talk about these diagrams, these can be Bayesian, you can formulate it in a Bayesian way. You can formulate it in a machine learning way, where you're like, yeah, x is a vector and y is a vector, and I kind of run like a fancy regression network on it. They can be images, they can be absolutely anything. I won't be talking about the details because you know them as well as me. No, it's machine learning. No, machine learning in that view just fulfills the role of characterizing dependence. And so instrumental variables, we're again in that situation with confounders. We're ignoring the colliders for the moment, again, because we will definitely not be correcting for them. The whole idea of instrumental variables is we assume that there's a very small part of the world that we understand. So here's the assumption that we have. There exists a thing that we call an instrument, the instrumental variable. That one must influence the variable that is the potential source of the causal effect. So I must have that the probability of X depends on what I do to that. The world is full of that. Right? You get, but then here comes the strong assumption. I need to know that this variable affects the rest of the world only through this potential, not anything else. And at the same time, I know that this thing must not be affected by potential factors. Can anyone think of a good instrument? Okay. Your birthday, exactly, wonderful. For example, it's very unlikely that if you're born towards the end of December, that you will fundamentally be more or less stupid than if you're born early in January. I mean, like, what you know is for all that we know, astrology could be true, but let's assume that it's not. Then I have strong assumptions that the late December babies are as intelligent as the early January ones. But then the school will react differently to, and many sports will react differently to being born late and being 1 year versus another. And then you can say this will therefore not, there's no reason to believe that when exactly you're born, late December versus early January, it will strongly change your ability of playing ice hockey. Like, why would that happen? But we do believe that it changes how your trainers react to you. And we can then use that to basically ask how like the establishment of training students affects their outcomes response. And the confounding goes away because kind of while these two are confounded, there's no relationship of any of them with like if you're born late December or January. That's the idea of instrumental variables. And now let's briefly see what the effect is. So if the assumptions are correct, you get an unbiased estimator out of instrumental variables. This is real, the estimated treatment. In fact, I should say this is a set of where we have like fun level tutorials on Jupyter books, and I believe there's a QR code like two slides. The real effect in this case too, we can see that we have an unbiased, that we get unbiased estimators for that. If we instead do regression, we get a biased estimator. So our causal effect can be arbitrarily wrong. But if we use the instrument and our instrument assumption is correct, then we get the correct unbiased estimate. I should also say like that bias is a big bias of the causality field. There's large branches of the causality field that demand unbiased estimators. And we can talk about why this is a good or bad idea. And now, if the assumption is wrong, it's not an instrument. There's something that still confirms it. So if you get treated, the instrument is something that does depend on possible conformance, then we get biases. Oh, and I should also say one more thing here. You probably saw that. The estimate of regression has lower values. And basically, when we do instrumental variable modeling, or for that matter, pretty much any strategy we use to improve causal validity, we are getting better causal validity, and we're giving up on some of the statistical power of that. And that's also what you see here. If our assumptions are wrong, well, then we have an extra bias because our assumption is wrong, and we have the extra bias. So we only want to do that if we really have good assumptions that this is a good instrument. And here's the QR code. Anyone want to play with these kinds of techniques? Have a look at this. It is really interesting how useful these methods are. And I'll be happy to also share the links later. So let's give an example. Does eating grains make ducks lay more eggs? The treatment is I give them grains. The outcome is how many eggs they lay. And now you can say, there's a problem. We can have a confounder, maybe heavy ducks like prefer grain and have more eggs, and we wouldn't know about it. We wouldn't know about it, but what we can do is we have an instrument. Maybe someone says, oh, we're going to offer grain to only the low weight ducks. And then we have that as, or like we will randomly. And but now there's a problem, and so yeah.
So does that mean that we use instruments for known confounders?
We choose, so the mindset of an economist is we go through the world looking for incredible instruments. Like basically we are looking for things in the world that affect other things. So where the first thing is basically random or something that is local, because as soon as you give me like a local injection of randomness, I can figure out how anything possibly affects anything else as long as it's downstream of that. Let's go through this example now. So this would be a perfect instrumental variable case, but now let me introduce the first complication to that. Now, like this is just standard instrumental variables. This is basically I look for randomness in the world to figure out how causality works. Yes. So, yeah. Yeah, so the first rule of causality is basically without prior knowledge, you can never learn about causality. Now, prior knowledge can take a specific form, which is if you allow me to interact with the real outside world. Right? This is also a channel through which I get prior knowledge. But yes, how do the economists find out that an instrumental variable is dead? Like I make believe, what do you know? Like who gets assigned to you as doctor is a great instrument because it's random. Well, but if it's not random, like the rich people get a different doctor than the poor people, then we're confounded. How do they find out? Well, shoe leather, machine, like all good data approaches are like shoe leather. You don't put everything through a magical algorithm. What you do is you call them. You're like, hey, you Penn, tell me exactly how each patient gets assigned to a doctor. And it turns out there are parts of the Penn health system where you do get assigned a random doctor. And there's cases where you can ask for a doctor or you get random assigned. And they actually have that in their records. So basically, these things go through, is this credible? Can I call people to obtain the knowledge? But so the idea of quasi-experiments is we're in this big complicated world that we can't understand. But here is an expert who can tell me about one local thing. And if he's not lying to me, then I can use that to basically learn about the cause effects that are downstream of that. Because we effectively have constructed a randomizer. You can use a coin toss if you're the almighty, because you can say, I throw a car, you get that doctor, we throw a car, you get that doctor, we can do those things. But the coin toss is something we can't do unless you give me access to the system. So yes, if I do the coin toss, that's a randomized control trial. That's the best thing I could possibly do. It's just, if we're honest as data scientists, we are not all that powerful. The big wide world is running, and the best we can often do is to say, okay, let's look at this one. And there's a lot of different ideas in the quasi-experimental framework where we can discover these random things. And if you give me random, anyway, I can figure out lots of causal things. But you need to give me that random piece. And it's fundamentally impossible. No, there is no, and there's provably no way of getting a causality unless you give me prior knowledge. You need to tell me, well, this is a random part. Now, imagine, take your context. You live in a world, it turns out unknown to you. There's the big boss of this simulation world who makes it so that your comments like predict that someone will get cancer, and then everything's out of the way. So you need to have that knowledge. There is randomness in this actual time. So if you want to understand the world from observational data, it's a hunt for randomness. And that randomness you can never discover. You need prior knowledge to get there. And of course, like if I can interfere with it, then I can do it. I can say, well, can I figure out the physics of how the coin flows or something? But there I'm using prior knowledge. Cool. So here's standard IV. Now, here's an interesting problem. What happens if you have non-compliance? And it turns out that in those situations, you almost always have non-compliance. Let's, for example, that we just said, I'm not eating grain. You can offer me as much grain as you want. I'm not eating, just to be clear. And there could be other ducks who basically say, well, look, I will always eat grain because I'm just a grain eater. I'm sorry. And then there's like the so-called compliance, like you offer them grain, they eat a grain. You don't offer them grain, they don't. And if you look at the domains where we're really interested in things, say medicine, public policy, you often find that compliance is absolutely correct. So I looked at a lot of medical data sets that are of the nature. And you go to a doctor, you say, everyone above AIC 6.5 is a diabetic, they need treatment. And then you look at like what's happening. Yeah, like at 6.4, most doctors, or like about a third of doctors will still call you diabetic and treat you as if you were one. And about like 70, about 40% of doctors, 50% of doctors, even if you're about that threshold, protect that you don't have to. And so non-compliance is a huge issue. So let's talk a little bit about non-compliance. So if we look at the variance of the IV estimator, you can say there is the variance of the outcome that we have for the compliance. But there is an extra factor, which is that you have the standard division by n, where this is the number of subjects that you have. But you have a p-compliance squared. What does that mean? That means that if you have a large number of people who don't comply, then the variance gets to be there. And in other words, this standard equation for what we have in this case. So now the intuition is, what if you have an oracle that tells me to do 5? But then my number n would get made by only that compliance. But he complied would get 1. So the idea here is it's like a very simple approach that machine learning can offer is if machine learning can tell us who will comply and focus on those, then I will have higher statistical power. And higher statistical power in medicine means you can actually see things that you could otherwise see at your trials cheaper and so on. Yes.
So if you exclude non-compliant, then and you're developing a treatment that works for all, can you go astray?
Yes. Wonderful question. We redefine the whole thing. We're basically saying there's compliance, and I can say things about compliance because we'll be using an IV here. There are non-compliance, but if we're honest, all bets are off for the non-compliance, so we don't know what's going to be non-compliance. Now, this is something that I would employ you. Well, tell me, and again, I'm asking for prior knowledge. Do you believe that these non-compliance are fundamentally the same, maybe because you believe the biology is conserved in something, or are they fundamentally different? And you can say, if I give you a drug for your heart, maybe the compliance and non-compliance credibly have the same physiology. Imagine the compliance are the ones who go to the gym if you tell them to go to the gym, and the non-compliance are the people who will not go to the gym, whatever. Those two groups are very, very different. We wouldn't want to generalize from the gym goers, we think. Yeah, send them an email in the middle of the day that maximizes the probability that they actually go to the gym. Then the non-compliance basically you can't generalize. So we redefine the problem. We say that we want to estimate the causal effect on the people that the oracle says are compliant. And we want the statistical power of that to be as large as possible. And here you can see how the number of exclusions of ducks that is positive in a simple case increases power until you have thrown out all the non-compliance, and then it decreases power because, well, you just lose units. And so you have an effective number of subjects, which is the n that you have times the proportion of compliance squared. So we have a good model of what we should be getting out of that. No, and in this case, we would only talk about the complier scale. Now we can have data-driven exclusion criteria. We can use observed features in machine learning to predict other sample compliance. So we're not predicting what the causing is. We're just predicting, will that doc do what we tell them? Will that patient actually do what we tell them? Or will the doctor basically ignore the guidance? Now, like, for example, I might want to optimize a policy. I might want to say, okay, at which threshold should I call you diabetic? Well, it will help you. If I can predict that certain doctors will ignore that threshold regardless of what we do, then they're not part of the compliance set. And it doesn't even matter that we so in case we can use observed features in machine learning to predict other sample compliance, and then we can estimate what type we have. So data-driven exclusion does improve. We have standard IV in low. We have data-driven exclusion in orange. You can see we always get significant benefits in power. Now let's try some real data. We take optimum data, regression discontinuity setting, A1C of 6.5. It's basically your blood cells carry with them a history of how much sugar they've seen in the past. Best interpretation, I guess, at this level of C. We know that a lot of doctors are very compliant for that. And then the follow-up, my outcome measure here is just the follow-up A1C. We first go there, we call them diabetic or not. That's our treatment. And the outcome is the A1C the next time they get the health system. Here you can see the full sample. You have 30-day diabetes diagnosis rate. At the rate threshold, they easy jump. But note that jump is just 0.65 because doctors are very, very non-compliant with those things. And then you can look at once we do that with by excluding the machine learning predicted non-compliance, and then we can look at these effects and we can see that they are also smaller. But that's just to say that it works. Here's the non-standard logic. Like the machine learning tells us who we are talking about, and then our predictions technically only apply to those. How we should treat the non-compliance then depends on the model that we have of how non-compliance actually works. Currently we do this thing where we look through large medical databases and we automatically pull out all the regression discontinuities that would be maximally powered. So we can now basically do all this pipeline automatically, where we can say, okay, let's go through all of medicine, find all the thresholds that exist, and find if we can use them to do causal effects. So now to come to something completely different, meta-learning causal discovery. And like what we had so far is we take what the economists and people in medicine already do, which is an ID or regression discontinuity, and we're like, can we use machine learning to increase the power? Yes, we can by excluding non-compliance. Here we ask, can we use machine learning to learn how to machine learn, and to just how to learn how to do causal effects. Standard supervised learning, I know they hurts, and I know for some subset the true outputs, and we get good at mapping from it. But
I have a question about the I guess
I am switching to something completely different.
But if you're using machine learning to predict who is compliant, so in data there is that feature is right. So why can't you do anything?
Yeah. So you mean like if someone is a complier, we cannot know that.
I mean that's been predicted from data. Right? So you are so then why can't you just use more traditional machine learning without worrying about
It's just the prediction of if someone is a complier is perfectly traditional machine. It's just that perfectly traditional machine learning solves a problem that is very specific to it. And the other thing that's a little tricky, like you can basically have it only partially observed, which is on the left of the threshold. You can only observe if I take it. If I don't take it, despite being to the left of the threshold, you cannot distinguish kind of a non-complier that is a never taker from a complier. And on the right side, you cannot distinguish an always data from. And so you have partially observed, so you ground truth, and therefore you need to make an assumption of continuity that you can say.
So to follow up on this question, so do you need additional data to discover non-compliers, or it's all
No, it's all on that same day. Yes, so we do that same track that Susan Apper uses for her honest trees, where we basically have an outside cross-validation loop, where we use one half to find out who's a complier, and then the other half to do what we want to do, and then we do it. So very good. And very, very fun. Yes.
So let's say I have like two clusters, one for compliers and one for compliers, like they probably could go to whatever. And I already include that allows me to decide in my list if you're a complier. And then I pass the machine learning framework, the new black box, those that are here. I feel like my black box is learned that some are compliant and some are not. And they both follow two different distributions.
So I'm not sure how you set up the logic system. Let me sketch how some people set up such logic, where they basically say, let's use the treatment variable here. Here, let's just give this and this to a machine learning system that predicts. That introduces very much because it doesn't use the fact that the IV has causal validity. It gives you low variance estimators, but it doesn't give you high causal validity estimators. So that's basically, that is the trade-off. Like you're then in that domain where you get low variance, but very heavily biased estimators. And how biased you'll be depends on kind of the covariance matrix. Cool. Okay. I know, rushing 5 minutes to get last. There's no more questions. Okay, so now, so when you saw what we did before, this is what's effectively happening. You have a human who understands. I'm like, call out after order. Do you assign the patient's random? Yes, no, like yes, then yeah, let's do something. So a human knowledge, and that human knowledge ultimately gives us an output. Then we get data, and then we get a mechanism pushes out an explanation of things for causal. But you all know the Victor lesson, no? Who doesn't know the Victor lesson? Who does know the Victor lesson? Rich Sutton's Victor lesson. Okay, now this is gonna, so the one observation of machine learning that Rich Sutton calls the Victor lesson is the history of machine learning is we use our wonderful, amazing minds and knowledge of the domain to build algorithms and kind of like use all the things that we know about the world and we're micrally part of us. And as soon as more data comes in, we do an algorithm that replaces the algorithm that we have by just doing machine learning with more data and then better for the human knowledge always only gives us a few years before the repeat data varies. So that is the big premise. So now that's applied to causal insights. You know, like these guys, I'm sure they're really right, the causal insights doctors that we follow, but like they're also wrong. I'm like a little bit. You know, and that's why the beta lesson is coming from. Like representations are kind of good about the world, but they're not quite right. And if you give them more data, then the data is going to be much better than the knowledge of use. And now let's phrase this as a learning part. Like we have input, we have, let's say, I give you lots of supervised plots where I tell you, here's the observational data, like this is like the time series. And here's truth. Here's how things, here's what happens if we actually reach in the system. And then let's have an algorithm that basically learns. Now it's just a mapping. Ultimately, it's a mapping from data onto causality. And we can discover that algorithm from lots of training samples. And now if we want to actually do that, I'll bring this in. not run out of power soon, but like maybe I'll run out of time before. Okay, now we take that with the system where we know causality, we have it's a microprocessor, we know how every transistor influences every other transistor because we have a net list of that. Now this becomes a causal discovery farm. I give you two transistors like this, or like this. This is the causal pair of transistors, the non-causal transistor. Why do we use the microprocessor? Because there's not any really good supervised causal data set in the world so far, and I'm working hard to change that. We use perturbations to define causality. Basically, we have the simulation of the microprocessor, and we simulate what happens if we just flip a transistor from off to on. And we also, of course, use honest validation. We use half of the data, we use half of the transistors to train an algorithm that does causal inference, and then we use the other half to see if it works. And we use a standard transformer system, like nothing before. And then what we find, here we see the area works really well at solving this inference problem, works much better than what humans do. Humans have this idea of linear informational range. What much worse than the non-causal inference. It's also super robust to noise, as you might expect from a neural network. It generalizes across gains, so we figure out causality using Donkey Kong, and then we test on spacing layers. Pitfall generalizes really well across that. Then, because it's stimulation, in principle makes a difference, and it does make a big difference. We can use GradCam to see where it matters, and in fact, what it does is that the one thing it kind of focuses on transistors. Like if one transistor drives the other transistor, we expect that this wave coming that goes from off to on, that switches one transistor, which then immediately switches the other transistor. And it focuses on that instead of the noise that we have. Now, what does this mean? The negative thing is we need lots of causal ground truth data. And it's impossible for humans to understand. Like instrumental variables, I can explain it to you. You get an impression thing. But if you think about it for a while. But if we have enough data, it will be better than anything humans do. And we can have meaningful proofs. They all basically derive from the standard proofs in machine learning. And it's a new approach to get into really messy observational spaces, but you need causal ground truth. Take-home message is, without the machine learning, have somewhat over. There's so much to learn in the schools that are there. There's a new conference that I'm one of the advisors of that. Clear. And then specifically, I showed you exclusion can be a meaningful data science problem, and maybe we should look for more to learn how to do causal inference. And with that, thank you very much.